So infinite series. So this is just the sum of all of the terms of an infinite sequence. And so these are the terms A1, A2, A3, A4, AN. So these are the terms, and this happens to be the nth term here, and then you keep on adding and adding and adding. And so we call this an infinite series or just a series. And so the A1, A2, AN are called the terms of the series, and N is called the nth term or the general term of the series, and the sum of the first n terms of a series is called the nth partial sum of the series. So if you want to sum from k equals 1 to n rather than from k equals 1 all the way to infinity, then you would actually go ahead and just call this Sn. And the sequence Sn is referred to as the sequence of partial sums of the series. And so Sn plus 1 is Sn plus An plus 1. In other words, the sum from k equals 1 to n plus 1 of ak is equal to the sum from k equals 1 to n of ak plus an plus 1. So you're just adding the one more term on. So for the convergence of an infinite series, if the sequence Sn of partial sums of the infinite series converges to a limit S, then we say that the infinite series converges and that its sum is S. If the infinite series converges and its sum is S, we write that S is equal to the sum from k equals 1 to infinity of ak, otherwise the series is said to diverge. So then actually we have the telescoping series, and then we'll have one more type of series, and then I'll just do some examples of these for the next few minutes here. So the telescoping series, if Bn is a sequence, then the series of the form, the sum k equals 1 to infinity of bk minus bk plus 1 is called a telescoping series. So the nth partial sum is given by, you can see it worked out, but it's b1 minus bn plus 1. So it's called telescoping because all of the terms other than the first one and the last one actually end up getting canceled out when you expand this. So therefore, if the limit is n goes to infinity of bn plus 1 exists, say that it's equal to L, then the limit of this telescoping series is actually b1 minus L. So here's an example. Tell whether the series sum from n equals 1 to infinity of 1 over n squared plus 4n plus 3 converges or diverges, and if it converges, state the value. All right, so what I'm going to do here then is I'm going to go ahead and I'm going to factor the denominator here, so that will be n squared plus 4n plus 3 is n plus 3 n plus 1. Then I'm going to use partial fractions on this. So use partial fractions here. So I'm going to rewrite this as 1 over n plus 3 n plus 1 is a over n plus 3 plus b over n plus 1. And then I'll use the basic equation method. It's up to you which method I guess you would like to use, but if I use the basic equation method, I have uh, n plus 3, n plus 1 is the common denominator, so 1 is equal to a n plus 1 plus b n plus 3. Then I'll distribute the a and the b. So 1 is a n plus a plus b n plus 3b. So this is over here 0n plus 1. So the coefficients of the n terms need to be set equal to each other. So again, this we're using the basic equation to get all of this. So that means a plus b is 0, and then we set the constants equal to each other. So a plus 3b is equal to 1. Then I'll multiply the first equation by -1 to get negative a minus b is 0, and a plus 3b is 1. I'll add these together, so negative a plus a is 0, negative b plus 3b is 2b, 0 plus 1 is 1, divide by 2, so b is equal to a half. And then since a plus b is 0, we know that a must be negative a half. So this is a and b here. So we have, let's see, so a over n plus 3 plus b over n plus 1 is negative 1 half over n plus 3 plus 1 half over n plus 1. So it's negative 1 over 2n plus 3 plus 1 over 2n plus 1. So I'm going to bring that back over here. So hopefully now you're seeing that this is just partial fraction so far. So do you have any questions, Maxwell? All right. So now what I'm actually going to do then is now this might actually seem like some strange way to do this, but if I look at this, then I know that the partial sums are going to be Sn is the sum. Now, well, one thing you can do though is I'm going to actually bring this 1/2 out in front. All right, so 1/2 times the sum of k equal 1 to n of negative 1 over k plus 3 plus 1 over k plus 1. Now, I'm going to write out the term so that you can see what's happening here. So it's 1/2, and then for k equals 1, I have negative 1 over 1 plus 3 plus 1 over 1 plus 1, and then plus what I get for k equals 2, which is negative 1 over 2 plus 3 plus 1 over 2 plus 1, then plus what I get for k equals 3, so negative 1 over 3 plus 3 plus 1 over 3 plus 1, plus what I get for k equals 4, so I have negative 1 over, let's see, where is it? 4 plus 3 plus 1 over 4 plus 1, and so on. So let me just make it clear that now what can you see here? Well, here I have a, a, a negative 1, this is negative 1/4, right? And this is 1/2, and this is negative 1/5, but this is actually what is that going to be? That will be 1/3, and this will be -1/6, and this will be 1/4, and this will be -1/7, and this will be 1/5. All right, so now let's cross out whatever terms that we can see are canceling out. So we know that the 1/4 definitely cancels out, -1/4 plus a fourth. The 1/5 definitely cancels out, -1/5 plus a fifth. And then hopefully you can see that the pattern, like if we do another one here, so I don't know how many that you want to do, but if let's just say I do one more just for like just to say that we for sure don't miss anything and that we get the pattern correct. I don't know why this whiteout is so cheap, and I know that I paid a lot for it at Meyer, and I don't have the normal whiteout that I get at the college even, so I'm using this cheap stuff from Meyer that isn't the oddly enough the college just buys Staples brand, and the Staples brand is better than the big name brand that you get at from Meyer. But anyway, so if k is equal to 5, I have -1/5 plus 3 plus 1/5 plus 1. So then that will be the -1/8 and 1/6. So then the 1/6 terms cancel out. Then if k is equal to 6, I get -1/6 plus 3 plus 1/6 plus 1. So I get -1/9 and 1/7. So here the 1/7 terms cancel out. So I hope that you can see the only terms that will be left actually are the 1/2 and the 1/3. So eventually, all the other ones will cancel out. So I need to go turn the light back on. It turned back off. So there, I was able to turn the light back on. So now I have to go and make sure that I understand what happens for the last several terms here. So if I do some more terms and then I get closer to the end, I see that if k is n minus 2, I'll get the -1 over n minus 2 plus 3 plus 1 over n minus 2 plus 1. Then if k is n minus 1, then I have -1 over in that will be n minus 1 plus 3 plus 1 over n minus 1 plus 1. And then if k is equal to n, I have -1 over n plus 3 plus 1 over n plus 1. And then this right here is actually negative 1 over n minus 2 plus 3 is n plus 1. Then 1 over n minus 2 plus 1 is 1 over n minus 1. And then -1 over n minus 1 plus 3 is -1 over n plus 2. And then 1 over n minus 1 plus 1 is 1 over n. And then we have -1 over n plus 3 and 1 over n plus 1. But you can see what terms hopefully will go ahead and cancel out here. So the n plus 1 goes away, and then believe it or not, what else goes away happens to be the the n minus 1 and the 1 over n term. So those would go away with this one over here. That would be when n is k is n minus 3. So 1 over n minus 3 plus 3. that would actually get rid of the 1 over n term, and then you have plus 1 over n minus 3 plus 1. All right, so eventually, yeah, that one will get canceled out, and then um, the 1 over n plus 2 will eventually get canceled out as well. So what you're left with then is, and I'll write it on a new page here since I realize I'm running out of room here. So then I'm left with 1/2, and then we had the 1/2 plus a third, and then minus 1 over n plus 2 minus 1 over n plus 3. So now we need, remember this was Sn, so we need to find the limit as n goes to infinity of Sn to see if the series converges or not. All right, so this will be the limit as n goes to infinity of Sn. So it's a limit as n goes to infinity of 1/2 times a half plus a third minus excuse me 1 over n plus 2 minus 1 over n plus 3. So now I can bring the 1/2 in front, and then the limit as n goes to infinity of a half is a half. The limit as n goes to infinity of a third is a third. And the limit as n goes to infinity of 1 over n plus 2 is 0. So that minus 0. And the limit as n goes to infinity of, excuse me, of 1 over n plus 3 is 0. All right, sorry, I just need a drink of water. I guess that's the disadvantage of working in the basement is that it's kind of dusty. All right, so this is a half, and then a half plus a third. If I find the common denominator of 6, right, 3 over 3 and 2 over 2, that's 3 over 6 plus 2 over 6, that's 5 over 6. So a half times 5 over 6, that would be 5 over 12. So I know then, therefore, the partial sums actually go ahead and the partial sums go ahead and converge to the 5/12. So therefore, we say that this actually converges. All right. So therefore, the series converges. All right. So, do you have any questions about that here? Right, yes. So that's all it is. So otherwise it would be divergent. So just try to remember that that this is uh that this is one of those things where um that this is what it converges to. All right, so therefore, Oh, you know what? I was going to say one more thing, and I'm trying to see what I know that I want to say one more thing about this, but I I was looking at um my calculator again to see if I want to say something else, but it it actually is one of those weird um weird things here. So uh oh no, I have a problem with my calculator. That's what it is. Because my calculator, I think I told you that the calculator was actually doing something weird. So, but remember that this actually isn't what the series converges to. This is what uh, the partial sums converge to. So if I wanted to look at, remember my original series AN, right, was sum n equals 1 to infinity of 1 over n squared plus 4n plus 3. But all I looked at was Sn, and Sn was the 1 half k equals 1 to n of negative 1 over k plus 3 plus 1 over k plus 1. And I said the partial sums converged to the 5 over 12. But then this one here, if I if I look at it, this one actually is is something like this one converges to some weird value that is so hard to find that sometimes we don't actually care what it is. We just care that it does actually uh, converge. It's like one. I just looked it up. 1/12 3 square root of the time pi hyperbolic cotangent of square root of 2 pi minus 7. So that's about 0.52769. So do you see why we wouldn't want to find that value, exactly? Because it would be almost impossible to to do this. But the partial sum here, 5/12, is only 0.41 uh, like 6, 7. So do you see that's not even really close to if we added all the values up to infinity? So that's what I just want to make sure that you are clear on that um that if I'm only looking for some of these um actually this isn't even I don't even think this is actually 5. This would be also what was your question then? Yes, yes, and that's why we need the the partial sums. Yeah, so um yeah, so that might seem like a little bit weird, but that is why we do need the partial sum, so that, because it will be easier to find this value over here than it is this value over here sometimes. Oh, I really hate the dust in my basement here, but all right. So now let's do another example. So, yes. So we'll I'll do the next two examples, and then I'll save the part on geometric series for next week. Um, that way, at least you have this part of the notes done before we get to the geometric series. So here we go. So you have the series here, n equals 1 to infinity of 2 over 4n squared minus 1. So this is actually, excuse me, very similar to the last one. So this is a series, and here's the associated sequence with that series. And I don't know why I changed back to the pen when I know that doesn't show up as well. But here's the associated sequence with that. So a n equals 2 over 4n squared minus 1. So we know that the sequence, the limit as n goes to infinity of 2 over the 4n squared minus 1 will converge to 0. So the sequence converges to 0. So now let's talk about the series here. So here we have the sum n equals 1 to infinity of 2 over 4n squared minus 1. If I factor that as 2n plus 1 times 2n minus 1. And then I can use partial fractions again. So if I have a over 2n plus 1 plus b over 2n minus 1. All right, so that's 2 over 2n plus 1, 2n minus 1. What will I get when I use the LCD here to find the basic equation? So the LCD is 2n plus 1, 2n minus 1. So if I multiply through by this gives me 2 is equal to a times 2n minus 1 plus b times 2n plus 1. So if I distribute the a and distribute the b, I have 2 is 2an minus a plus 2bn plus b. And then I have 0n plus 2 over here, so I equate the coefficients. So 2a plus 2b is 0. And for the constant terms, I have negative a plus b is equal to 2. I'll multiply the second equation by 2 to eliminate the a's. So 2a plus 2b is 0. Negative 2a plus 2b is equal to 4. Then I'll zero out the a's. So 4b is equal to 4. And if I divide by 4, b is equal to 1. And then since negative a plus b is equal to 2, that means that a has to be a negative 1. So that means 2 over 2n plus 1, 2n minus 1 is a over 2n plus 1. So that's negative 1 over 2n plus 1 plus b over 2n minus 1. So 1 over 2n minus 1. And then I can rewrite the series as the sum n equals 1 to infinity of 2 times negative 1 over 2n plus 1 plus 1 over 2n minus 1. And so I know then if I look at this, I can actually, I don't even know why I wrote the 2 there, because I thought I had another 2 for some reason, but I do not actually, do I? Nope, I don't have another 2, so that's good. So now I can write down the partial sum. So therefore, the partial sums are going to be Sn is the sum from k equals 1 to n of negative 1 over 2k plus 1 over 2k minus 1. So then if I go about my business here and just rewrite these terms out, just like in the last example, if k is 1, I get negative 1 over 2 times 1 plus 1 over 2 times 1 minus 1. And then if k is 2, I get negative 1 over 2 times 2 plus 1 over 2 times 2 minus 1, and then so on and so forth. So if I go one more term, so k is 3, negative 1 over 2 times 3 plus 1 over 2 times 3 minus 1, and then all the way to the end when k is equal to, say, n minus 1, I get negative 1 over 2 times n minus 1 plus 1 over 2 times n minus 1, and then plus the nth term, so negative 1 over 2n plus 1 over 2n minus 1. And here I can see I have negative 1/3 plus 1, then this way negative 1/5 plus a third, then negative 1/5, or is it 1/7? 1/7, yep, plus a fifth. And then I can see that the 1/3s get eliminated, and the 1/5s get eliminated, and the 1/7 will get eliminated with the next term out. So the only thing I'm left with is the 1. And then for the terms with the n's in them over here, I have, if I distribute the new denominator, 2n minus 2 plus 1 is 2n minus 1. Then 2n minus 2 minus 1 is 2n minus 3. Then I can see that the 2n minus 1 term will get canceled out, and the 2n minus 3 term would get canceled out with this one over here. So I'm actually just left with this term right here. So this simplifies to 1 minus 1 over 2n plus 1. And then I can go ahead and find the limit as n goes to infinity of Sn. So that's the limit as n goes to infinity of, let's see, 1 minus 1 over 2n plus 1. So that will be the 1 minus the limit as n goes to infinity of 1 over 2n plus 1 is 0. So 1 minus 0 is 1. So therefore, the series sum, the original series, sum equal 1 to infinity of 2 over 4n squared minus 1 converges. All right, so do you have any questions about this one? Yeah, so these ones were both sort of telescoping series, but I'll do 2 quick examples of ones that are not telescoping series, and then we will be done here. So tell whether the series converges or diverges, and if it converges, state the value. So the part that we have here is actually 1 over 2 to the n. So here I have n and 1 over 2 to the n. So we have, if n is 1, I get a half. If n is 2, I get 1 over 2 squared is 1/4. And then if n is 3, 1 over 2 to the third is 1/8. And if n is 4, I get 1/16. N is 5, I get 1/32. So then the partial sums are S1 will be a half, S2 will be a half plus a fourth will be 3/4. S3 will be a half plus a fourth plus an eighth, that's 7/8. S4 will be a half plus a fourth plus an eighth plus a 16th, that will be 15/16. And S5 will be a half plus a fourth plus an eighth plus 16th. That's a 31 over 32. So then I need to find Sn. So I can tell then that this is going to be 2 to the n minus 1 over 2 to the n. All right, so you can see that that's 2 to the first minus 1 over 2 to the first, 2 to the second, minus 1 over 2 to the second, 2 to the third, minus 1 over 2 to the third, 2 to the fourth, minus 1 over 2 to the fourth, 2 to the fifth, minus 1 over 2 to the fifth, and so on. So now, now that we found the formula for Sn, now we need to find the limit as n goes to infinity of Sn. So it's a limit as n goes to infinity of, let's see, that will be 2 to the n minus 1 over 2 to the n. So I'll just go ahead and rewrite this as limit as n goes to infinity of 2 to the n over 2 to the n minus 1 over 2 to the n. But 2 to the n over 2 to the n will be 1, so 1 minus 1 over 2 to the n. But that will be 1 minus the limit as n goes to infinity of 1 over 2 to the n is 0. So 1 minus 0 is 1. So therefore, the series converges. So that would be the series, the original series also converges. So in both of these, I actually wrote out the terms to find the formula for Sn. Like in the last example and in this example, I wrote out the terms to find Sn. But this example was a little bit different because none of the terms sort of telescoped out. And then the last example here, the sum n equals 1 to infinity of 1. Well, this is just 1 plus 1 plus 1 plus 1 plus 1, and it will keep on going until you just add it up to infinity, and so therefore the series diverges. So that's all I have on this, and that was, I guess, it.